Alright, so this is the first of several videos on the material in section 4.2 of the textbook on some of the sort of algebraic theory of vectors in n dimensions. So there are going to be several concepts that we're going to introduce over the next few videos, and they're all fairly abstract theoretical concepts, and they're ideas that take a little bit of time to get the hang of, so don't worry if the first time you see it you don't quite understand what's going on or you don't get it immediately. It takes time to get the hang of these things. So we're going to introduce subspaces in this video. In the next one we're going to talk about span, after that linear independence, and finally basis. Right now we're just going to introduce these ideas conceptually. We're not going to do very much with them because in order to kind of handle things computationally, you need techniques for solving systems of equations, which is coming up in chapter 5. So before we get to solving systems, we're just going to introduce these ideas, and then we're going to come back to them again once we have techniques for solving systems. We're going to come back to these ideas 2 or 3 times in the hopes that by the third time you'll be familiar enough with these concepts that you kind of get a feel for what's going on. It helps going through this material to have some good geometric intuition for what's happening, which is why we've already kind of gone over vectors in R3 and vector geometry. We'll see that for this topic of subspaces in 3 dimensions, the main examples you want to keep in mind for subspaces of R3 are going to be lines through the origin and planes through the origin. You explored this somewhat on your second assignment, the last problem on the second assignment. Essentially what that second assignment was asking you to do was to establish that lines and planes through the origin are indeed subspaces. We'll see that as we move forward through this video. Okay, so what is a subspace? So a subspace, first of all, is a subset. So remember, subsets were introduced way back in chapter 1. It was considered some of our review material. We covered this in the very first week. A subset is just, some collection of objects which is contained within a larger set. So in this case, our large set is Rn. And so when we say that U is a subset of Rn, we mean that U is some collection of vectors or points in Rn, depending on how you want to view things. But we're going to view elements of Rn here as vectors. So it's some collection of vectors. They're all n-dimensional vectors, but we're not necessarily considering all possible vectors in Rn, only some vectors in Rn. And what makes a subset a subspace is if if you look at those vectors in that subset and you check all of these 8 axioms for a vector space, right? The associativity of addition, commutativity of addition, existence of zero, distributive properties, all of these guys, that those properties hold when you apply them only to the vectors in the subset and not to Rn as a whole. And so it turns out that most of those properties are sort of automatic because you're using the same addition and the same scalar multiplication. We should probably specify that when we say that it satisfies the 8 vector space properties, we've already defined what it means to add vectors in Rn and to multiply a vector by a scalar in Rn. We're using the same addition and the same scalar multiplication. We're just not adding all possible vectors. We're only adding some vectors. And it turns out that the only thing that can really go wrong is that you add 2 vectors that are in your subset and you end up with something that is no longer in the subset, or you multiply by a scalar and you get something which is no longer in the subset. So there's one kind of base condition, which is that U has to be non-empty. And that means that it has to have at least one element. There has to be at least one vector in there. And usually what we do, because we know that every vector space needs to contain a 0 element, generally what we do here is we check that the 0 vector belongs to U. So if the 0 vector is in there, then we know that there's at least one vector in there, so it's not empty. And the 0 vector is a good one to check because it has to be in there. The next one is that U is so-called closed under addition, and U is closed under scalar multiplication. What do these closure properties mean? So property 2 just means that if U and V are vectors in U, then U plus V is also a vector in U. 3 means that if U is in U and C is any scalar, then C times U has to be in U. Okay, so if you have one vector in there, then you have to have every scalar multiple of that vector has to also be in the set. Okay, so this is basically what the third condition is saying. So one of the things that tells you, just kind of think about the three-dimensional picture. If you have one vector that's in there, right? So there's, say, your U, right? Then every scalar multiple of U has to be in there. So we can multiply by positive scalars and get other vectors that are in this direction, right? We can multiply by negative scalars, get vectors that are in that direction. It means that, well, basically, the position vector for every single point on that line through the origin in the direction of U has to be included in the subspace. So if U belongs to the subspace, then every point along that line in the direction of U also belongs to the subspace. And then if you were to add another vector V, right? So let's say I threw in a V. Maybe V is here, right? Well, then U plus V would have to be in there. So we would do our tip to tail rule. U plus V has to be in there. Well, in fact, U plus V has to be in there, but also any scalar multiple of U has to be in there. Any scalar multiple of V has to be in there, and so that would mean that in fact, any linear combination, anything that looks like, say, A times U plus B times V would have to be in there. And so if there's a second vector V in there, then in fact what you would get is you would get the entire plane that contains those two vectors, right? And that would be your subspace in that case. So we'll explore these ideas going forward. All right. So first thing we're going to do is we're going to just check to see, okay, here are some subspaces, right? We're going to define some sets, some subsets of vectors in R2, and we want to understand whether or not these guys are subspaces. So the first one is a set of all vectors of the form x and x squared. So in other words, what we're saying here is that if v equals xy, and that's an element of say u, implies y must be equal to the square of x. So we might ask, okay, is that guy a subspace? Well, we can see that the zero vector belongs to the set. So no problems there, right? I can set x equal to 0 and I get the vector 0, 0. Is it closed under addition and scalar multiplication? Well, let's consider. We could consider the vector 1, 1. That belongs to U. Right, because 1 squared is equal to 1. But if I did 2 times 1, 1, that would be 2, 2, right? That does not belong to my set because, well, why not? 2 squared is not equal to 2. We know that. 2 squared is equal to 4. And so we've just given an example of a scalar multiple which doesn't belong to this set, and that guarantees that this can't be a subspace, right? Because it's not closed under scalar multiplication. Now, what about the next set? Set of all vectors such that x plus 2y equals 1. Well, we know what that looks like kind of graphically, if we think of vectors, if we identify vectors with points, then what we're dealing with here is we're dealing with a line, right? This is basically a line x plus 2y equals 1. Right. And one of the things you'll notice about this line is that it doesn't pass through the origin, right? 0 plus 2 times 0 is equal to 0, not equal to 1. So the 0 vector is not in my subspace, and if the 0 vector is in there, it can't possibly be a subspace. So that means that this is not a subspace, right? And same here, this is not a subspace. All right, what about our last example? Set of vectors of the form 2t and minus 3t. Well, one thing you might notice off the bat, and this will be a useful observation going forward into the next video, is that a vector of the form 2t and minus 3t, we can write that as simply t times v, where v is the vector 2 minus 3, right? Okay, so now if I had, say, well, first of all, we notice that t equals 0 gives the 0 vector in U. And if so if I had two vectors, say u1 equals t1v, u2 equals t2v, if they belong to U, well, that would imply that u1 plus u2, so that's t1 times v plus t2 times v. I can factor out the v. I can write that as t1 plus t2 times v. It's still of this form, scalar times v, right? So in this case, t, this would be t. Right? T would be equal to t1 plus t2 in this case, right? If t1 is a real number, t2 is a real number, then t1 plus t2 is also a real number, and the condition here says t could be any real number, and so that means that this sum also belongs to U. And then similarly, you could check that, it's closed under scalar multiplication. Why is it closed under scalar multiplication? Well, if I did say C times TV, that's equal to CT times V, right? And so then again, C times T is going to be a real number, so C times T all multiplied by V, that is something of the proper form, and that tells you that your set is closed under scalar multiplication as well. So this guy is a subspace. All right. Notice that that in this case, our subspace, it's the set of all scalar multiples of a single vector. That's going to be a very kind of common observation for a lot of subspaces. This would be an example of what we might refer to as a one-dimensional subspace, because there's one vector that generates the entire set, right? This vector v, every other vector in the set can be written as a multiple of v. So there's one vector that kind of produces every other vector. Okay. So here's another example. What if we had two vectors? So that final subspace example we just dealt with, there was a single vector that generated the entire set. What if I had two vectors generating the set? Right? Now I'm not saying anything about what these vectors are, but let's suppose I have these two vectors. I'm going to consider the set of all vectors of the form a times x plus b times y. So all possible linear combinations of these guys. We want to show that this is a subspace. So let's call this set, we'll call this set U. And so we check. So first of all, if I set A and B equal to 0, well, that's going to give me the 0 vector. All right, so the 0 vector is an element of U. And now let's suppose that I have, let's say V is, let's say, AX plus BY in U, and W is, let's say, CX plus DY in U, right? So A, B, C, D here, all scalars, right? So in this set U, I can choose any values that I want for these scalars A and B. So C and D might be different from A and B. And what do I get for V plus W? So I start with AX plus BY, CX plus DY, right? But using the properties of vector algebra, I know that I can rearrange this equation. I can group things together. I can write this as A plus C times X, and then B plus D times Y. And this guy is again going to be a real number. This guy is going to be a real number. And that tells me that this is an element of U. And finally, we can also notice that if I do say K times V, that's K times AX plus BY. And if I distribute the scalar multiplication and group things together, I can write that as KA times X and KB times Y. And again, K is a real number, A is a real number, so K times A is a real number. This is a real number, and that tells me that this is also an element of my subspace. Okay, so that tells us that this set is indeed a subspace. So any set that is kind of generated in this way by considering kind of every vector that's generated by those two vectors is going to be a subspace. And if you think back to chapter 3, remember when we presented the vector equation for a plane in 3 dimensions, you might notice that what you have here is in fact a plane that passes through the origin, right? If you think of a plane described in terms of its vector equation, you would get all possible points that are of this form, right, for 2 vectors, x and y. Okay, so a plane through the origin also looks like a subspace. These types of sets, we'll talk about this in the next video. The way we might describe this is we say, well, this set here is what's called a span. This is the span of the vectors x and y. And it will be true in general that the span of any collection of vectors is a subspace, and we'll explore that in the next video.